Hello. All right, so here's a quick summary of way back at the start of the term, first term, when we went over special relativity. So I'm just going to go over these just to remind us what they were. So special relativity, we have time, mass, length, and how to add your speeds. And then last of all, we had E equals mc squared. So what did we learn in Physics 12 for special relativity? Well, overall, we knew those first two rules, where one, c is the speed limit, pretty much, and the other rule was the mechanics work in all frames of reference. You just have to know what frame of reference you're working in. All right, so we have time here, and we have this equation. So how to use this equation? Well, we know that the speed of anything is less than c, so therefore this fraction is going to be less than 1, and 1 minus less than 1 is less than 1, and the square root of anything less than 1 and positive is going to be less than 1. So that means overall, in the end, our t is going to be greater than t naught, always, okay? And when they talk about time, they call it time dilation. But essentially, how we remember this is the person, if you remember Speedo and Goslow, the twins, if you're going on your spaceship to a planet, traveling really fast, that person in the spaceship is going to feel less time has passed, or less time has passed actually for them. So since t is bigger than t naught, the time this person felt is less than the time this person felt. So this one is usually the Earth person, and this one's usually the traveler time. Okay, so t naught is the proper time, or it means the time that the traveler feels. So an example here is a 0.7 c spaceship, or 0.7 times the speed of light a spaceship is going. If we use this equation, we can kind of know the time differences between people. So 0.7 c spaceship, that will be in for our v there. So let's just try this out. T equals t naught over square root of 1 minus v squared over c squared. Instead of v squared, let's put 0.7 c, so it's going to be t equals t naught over square root of 1 minus 0.7 in brackets c squared over c squared. We know the c's are going to cancel, and that's going to be 0.7 squared. So 1 minus 0.7 squared rooted, so let's do that. 1 minus 0.7 squared. We know we're going to have to take the square root of that. So we're going to get this number on the bottom of the fraction. Let's just switch it to 1 divided by that, because it's on the bottom of the fraction. And we get 1.4, so on. So overall, I know my equation is t equals 1.4. I'm going to just round to 0, t naught. So overall, whatever time the person in the spaceship feels, the person on Earth will think it's 1.4 times longer. Okay, so that's kind of a brief thing on time dilation. So if I were to plug 1 hour there, the person on Earth would feel 1.4 hours have passed. Okay, if it was if this person went for 1 year, this person would feel 1.4 years have passed. Okay, so that's time dilation, very briefly. So mass here is very similar. So you have this m naught, this m, and then the equation here, you know this bottom's less than 1. So that means, just like the last one, m is going to be greater than m naught, always. Okay. The one thing to remember really with mass is the moving thing is heavier. Remember that, you won't get this question wrong generally. So if a 0.7 c spaceship is moving, its mass is, I'm going to do this equation, but we're going to plug in 0.7 c So you can bet if I put 0.7c in for v squared, the same thing's going to happen, where I end up with m equals 1.40 m naught. So I'm just going to go ahead and skip to that part. So now we have that the mass of something is 1.4 times the mass of the same thing in a different frame of reference. So which one is which? Well, this is how I kind of remember. Moving things are heavier. Okay, and since this one is 1.4 times that one, this one's going to be the heavier one. So this is the traveler's mass in reference to Earth. Okay, so the person on Earth will measure the mass of the spaceship when it's moving, and it'll be higher than if you measured it when it's still. Okay, or I guess this is the mass of the spaceship in reference to the person in the spaceship. In reference to spaceship. Okay, or it can also be known as, if the spaceship was still on Earth, what would its mass be? Okay, so this would be the mass we would measure if it was still, but it would be 1.4 times that if it was moving. Okay, but note that if it's moving really fast, if the person in the spaceship is weighing the spaceship, they'll still think it's m naught. Okay, you have to be outside the spaceship and see it traveling by to see that it will weigh more. Okay, so this time m is greater than m naught. All right, so now we move on to lengths. Lengths is a bit different. You have L equals L naught times root 1 minus v squared over c squared. This time it's not over. So we know this whole thing is less than 1. So that means L naught times less than 1 means that L is less than L naught, or L is less than L naught. Okay, and it says length contracts. That's how I remember it. Length contracts when things are moving. So an example is a spaceship's length will contract when it's moving really fast past Earth in reference to someone on Earth. So an example here is a 0.7c spaceship. Let's do the math again for this part. We would go, the root part is 1 minus v squared, which is 0.7 squared, c squared over c squared, and those will cancel out. So it'll be 1 minus 0.7 squared, root answer is going to be 0.71. I'm not going to go 1 over that because this time it's on the top and we don't have to do that. So this time it's really our L is 0.714 L naught times L naught. Okay, so this time the length contracts to 0.714 times the original length if it was not moving. Okay, and this also happens too when you're on a spaceship and you're traveling past, like, say, planets. The two planets' distances will contract when you're inside the spaceship moving really fast. But overall, it's this. Which one's which? L is going to be the contraction length, or the length of the moving thing in reference to still thing, while L naught is going to be the original length when it was not moving, or it's going to be the length of thing in reference to itself. Okay, so it's really its original length, or its length when it's still, and then L is its length in reference to something else, seeing it move. Last of all, we have additive vectors. We have v total is v1 plus v2, and then we have 1 plus v1 v2 over c squared. So what is this really? Why do we have this equation? Well, we just want to know what happens when you have a 0.7c spaceship that shoots a 0.7c rocket relative to the spaceship. how fast would it be going? Because we know c is the speed limit, and if we just add those two vectors, it would be 1.4 c, which is more than c. And we know c is the limit. So really, it's just that. It's an equation so that we can add those together. It's the real way to add vectors. It's not just v1 plus v2. It really should be v1 plus v2 over 1 plus v1 v2 over c squared. The reason why we don't do this normally is because it's generally the bottom doesn't matter when you're going at such low speeds in reference to c. So an example here, 0.7c, 0.7c, you just add them together via the equation. So it'll be 0.7c plus 0.7c over 1 plus, and this is 0.7c squared over c squared. You can bet the c squareds are going to cancel out, and it's going to end up with 1.4c over 1 plus 0.7 squared. So it's really going to be 1.4 divided by 1 plus 0.7 squared. And we'll get 0.94, and that c is still there. So really, if you do that, its relative speed will be 0.94 c. It'll never be more than c, essentially. Okay. All right, and so all this came from Einstein. We have the last one. His famous equation is the energy of something is its mass times c squared, because its mass kind of tells you how the atoms, I guess, are. So usually the equations that we see for this thing, in reality, is a real equation is mc squared, and it's still over this gamma thing, 1 minus v squared over c squared. It's still over that, but we don't really use that equation. We'll just use the equals mc squared, which just tells you the energy of particle. So it'll be like, what's the energy of 1 gram of anything? So it doesn't matter what the thing is, just the mass matters. And you just go 0.001 times c squared, and we know c is going to be 3 times 10 to the power 8 meters per second. So the amount of energy you get in joules is going to be a crazy amount. Let's just do it. So 3e8 times 3e8, you get 9e to the 16, and then it's times the mass of the thing, whatever it is. So this is going to be times with 0.001 because it's just 1 gram. So it's just a crazy large amount of joules of energy. So if you could get all the energy from something, you'd get a lot. Okay, I'd be able to power a house for a very long time. You could probably calculate that, but I'm not going to do it right now. So that's really our first unit, really quickly, the basics on what we did, just so you can relearn that. Thanks.